Alright guys, well welcome back, and we're now going to work on 2.6 number 21. So I'll put a big 21 there. And okay, so let's write out that function. You can see it right there, it's piecewise. Don't be scared of the piecewise functions, folks. And we have f of x equals x squared minus 1 over x minus 1. X cannot equal 1. And we're evaluating a equals 1. And then we have the function 3 if and when x equals 1. And they're asking us to determine on that function, look up here at the instructions, determine whether the following functions are continuous there. And then you use the checklist, so use formal justification to make those determinations. So let's go ahead and do that. And so we do know that there is a point f of a, and that f of a equals 3. So we know that that checklist works. Our next continuity, so condition 1 is okay. We're all good with condition 1. Now let's look at condition 2. Remember, this is the classic function I keep giving you. Okay, and so this guy looks like x plus 1. So this part of the function looks like regular old x plus 1, but it has a hole there, okay? So you have to evaluate f of a when a is 1, like they told us to do. So f of 1, I could say if I wanted to as well, equals 3. You have to evaluate it on the piecewise branch that contains the domain that they've asked you to evaluate. So I evaluated here. Now let's look at the next, and then also just remember what this looks like. And so first you have this, and then you have this, and it's defined at 3. So I have some other stuff I need to do, so let me stop that. I'll do that momentarily. And so it's defined here at 3. So that's what this whole piecewise picture looks like on the plane. So now looking at the second condition, we can see the limit as x approaches a of f of x does in fact exist. The limit from the left to here and the limit from the right to here do in fact happen to be equal to some limit constant, some constant number value, which in this case would be L is equal to 1. Right, so condition 2 is also a check. The problem is there for condition 3, because the limit as x approaches, you can see that right here, 1 and 3 are not the same thing. So the limit as x approaches a of f of x, which equals 1, does not equal f of a, we have a here, which equals 3. Therefore, the function is not continuous at x. Oh wait, did I pick the wrong point? Hold on, did I pick the wrong point? We might have to do this video over again. Did they say to pick 1? Or did I just write it backwards? Hold on, let me pause and check and see if this video is salvageable. Okay, barely salvageable. Sorry about the mistake there. So the first mistake is that the limit is going to be at 2. And that's because when I plotted it up here, take that original plot and scratch it out. Sorry, no ninja ducks while you're watching me in real time, but I made a little boo-boo here in the plot. Remember, it crosses, the x minus 1 crosses out, which means it looks like this for all practical purposes, so it goes through 1. So, and then at x equals 1 is where the denominator would equal 0, because 1 minus 1 is 0. And that, therefore, which would normally be at a height of 2, can't actually exist, so there's a hole there. And then instead, this part of the piecewise function puts the point at 3. So that then revises 2 of our answers. Condition 2 fails not because it's equal to 1, but because it's equal to 2. So I just had the limit wrong, and then we see that 2 does not equal 3. We also revise that down here. So the two-sided limit is equal to 2. The point defined at f at that value of x is equal to 3. 2 does not equal 3, therefore the function is not continuous at x equals x. Now, I always have students who say, but isn't it continuous at like like every point on x here is defined, has a defined point f of x, and this one has a defined point x, which takes care of all the ones up into here, and all the ones after are also defined, so shouldn't it be continuous? Remember, continuous, and the answer is no. Continuous means, in this case, as a technical term, exactly what it means in common sense. It means you can continuously draw it without picking up your pen. But I have to pick up my pen here and put it here, which means it's not continuous. And then after I sketch that in, I have to pick it back up and put it down here. So continuity or continuous functions are based on the pickup. A good fundamental tool is the pick up your pen or lift your tool, if you want to think of it digitally. So lift your tool. Do you have to pick up your pen? Do you have to lift your tool? If you do, you're not continuous. So we know that this one's not continuous. Proving it and narrowing in on why it's not, seeing which parts are okay and can be aspects of continuity. This can be a part of continuity. This can be a part of continuity. But if this one's violated, then these two don't matter and it's not continuous. You need to have them all, okay? And so when you have them all, you have the recipe for continuity. And I will say that these definitions, this is the range, good old-fashioned way of thinking of functions in terms of range. And then we add some limits to that. And now we have a whole suite of stuff that includes limits, which allows us to assess whether functions are continuous or not. Okay, so that was 21. Our next problem now is going to be 28. So I will stall and leave that up there. I hope everybody's doing really, really well. I will send a picture of what my hotel room looks like to you guys so you can see where I'm hunkered down. But I hope everybody's doing well. And again, I can do tutoring in the evening, so hit me up for some times, and we'll go from there. I'll make some other announcements, like remembering to send me whatever questions you want to go through in the first part of Chapter 2 for deep dives this week. You need to send me that as lists, and so on. So anyways, good successful stalling on my part there to get us to 28. Let's take a look at that. And what I would do is just remind you again, pause the video. I'm going to do the same thing just so I can get my notes in order and have these videos be efficient. But you guys pause the videos and try to do 28 on your own. And again, you're determining the intervals on which it's continuous. So here, you're not saying where it's not continuous. You're not saying why it's not continuous there. You're plotting the function, getting a sense for what it looks like, and then telling us where it's actually continuous and where. And so by definition, you'll know where it's not. But the answer is to tell us where it is in fact continuous. All right, so let's go ahead and do that now, and I'll do the same. All right, guys, so now we have 28. Let's go ahead and bang this one out. So the first thing is we want to not be reliant on technology. So let's go ahead and try to factor this. So 1 and 3, negative, negative. And here, that's a difference of 2 squares. Those cancel out, so we know that we have a whole at x equals 1. And then we know from this guy that we have a rational equation. And we know a few things about this. Oh, sorry for not moving that down, but it didn't really get in the way. We know a few things about this from our pre-calculus rules. The degrees are the same, and when the degrees are the same, you're going to have a horizontal asymptote at the ratio of the coefficients of a leading degree, which it's both 1 and 1, and they're both positive. So y equals 1 will be a horizontal asymptote. So I can sketch that in right away and say y equals 1, horizontal asymptote. I also know that I have no definition at x at positive 1. So I'll just, make a note. I'll put a tick mark there, kind of remind myself. And I know that at 3, at x equals 3, I have a 0. So what I'm doing, so I found my horizontal asymptote. What I'm doing now is I'm finding my x-intercepts. And my x-intercepts are going to be where the whole function equals 0. And the whole function will equal 0 when x is 3. And that helps me know that I have a point right here. And that's going to be really helpful for sketching the thing. And now we're going to plug in our asymptote, which is at negative 1 here. And so now we have that. And now we can do some test points and you can get an idea of what it looks like. So in order, I factored it, I found out where I have holes, I found out where I have a horizontal asymptote, I then plotted where I have a vertical asymptote, I then found my x-intercept, so horizontal asymptote, x-intercept, vertical asymptote, which is where the denominator equals 0. You do all of those things, you plot them out, and now you should be able to develop some test points and have a sense for what this function looks like. Maybe some points after this, and maybe some points before this, and just have a sense if it's like this or something. Maybe a point down here or so, and get a sense for what it's looking like over here. Maybe a nice easy point like -100, and then a point like just to the left of this, like -2. Test those out. I'll pause the video, you pause the video, let's do the same thing, and we'll come back with a clearer picture of what's going on. Okay, so let me take you through the test points I did, and then I'll sketch in the curve with you. So I jotted my test points down here, and the test points I did for the right branch, so I split it into 2 branches. I said we have stuff on this side of the asymptote and stuff on that side of the asymptote, the vertical one, because you can't cross it. So I split it into 2 logical things as follows. And then I said, okay, we know we're going through 0 here, so what's happening to the right of that at x equals 4? I then plug in 4 here, and I see I get positive over positive. So I kind of know from then, if this is a horizontal asymptote, that I'm going to approach it like that. There's nothing in here oscillating, so it's smooth and continuous. And this one will just converge on that asymptote. And then if we plug in x equals 1, we can see we get negative. Negative up here, positive down here. And so we know we're going to converge then on that asymptote there. I did, in full disclosure, I plugged in 2 points before I realized, oh wait, of course it will always be positive. So anything to the left of, so -1 is right where your asymptote is here. Anything to the left of -1 will be a net negative answer down here. And a negative minus another number will always be negative. So this branch here will always be a negative divided by negative, which is always a positive. So once you see that branch down there, and once you realize, once you get a little bit more familiar with these in pre-calculus, you have something like that going on. Of course, none of this is exactly to scale. That's not what we're trying to do. We're just trying to sketch this. And so now that we have a sense of what's going on, we can say that our continuity, okay, again, we're not supposed to just be like using a calculator and like being like, okay, yeah, that's where it's continuous. You're supposed to be refining all of these skills, leveraging test points, remembering the steps of curve sketching from pre-calculus, and then declaring the continuity using these logical and algebraic steps. And so our intervals of continuity are -infinity to -1. And then we cannot forget that at the point 1 right here, I'll emphasize it by putting in that, we have a hole, okay? So the other interval of continuity is going to be from -1 non-inclusive, because it's an asymptote, right here, from would be this portion up to that hole, up to 1. And then one more interval of continuity, I'll put another union down here and just wrap it around, and that's going to be from 1 to positive infinity. And so that's where we have our intervals of continuity. So you don't just take this, throw it in a calculator, and then be like, peace out, I'm done. First of all, you're probably going to miss this because the calculator or graphing tool won't tell you that. You'll get that there's an asymptote here, but you might miss this. Might miss that there's 3 intervals of continuity here because you might miss the hole. You might forget that holes happen where we can't divide by 0, but where it cancels out, and that vertical asymptotes are where nothing cancels out, and whatever we're left with actually is a vertical asymptote. A hole, I kind of think of it as a vertical asymptote that collapses to just a single undefined point instead of a whole, asymptote or something like that. And then at the very end, to use our principles of curve sketching, to use our pre-calculus rules to find the horizontal asymptotes, to remember good old-fashioned things from Algebra 2, like finding our x-intercept, finding our exclusions for our vertical asymptotes, which is really a third step. Sorry, I wrote part of it here, which is finding the vertical asymptotes. Finding the x-intercept is when f of x equals 0. So that's when the whole numerator will be 0. So like if I just plug 3 in here, it doesn't matter what happens anywhere else. If I plug in 3 here, it doesn't matter what happens anywhere else. It's equal to 0, and we're good to go. So there we go, intervals of continuity, and 28 is done. And I believe we are now done with this section. So great news. All right, we'll see you in the next homework section, guys.